harmonic motion. Okay, so oscillating motion. So may we call this repeat itself regularly. So that is paulit-ulit. Just like we call this simple pendulum. So you see here an image of a simple pendulum, no? So we have your bulb, okay, this one. So as you try to put it in an extreme position, so we have an oscillating back and forth of motion. So it is in an oscillating motion. So that can be display considerably irregularity. So if there is a grounding motion during an earthquake. So if the motion are repeated after an equal interval of time, so we call it, so it is called a periodic motion. Now, the simplest type of periodic motion, we call it the harmonic motion. Now this figure shows a demonstration of a simple harmonic motion. So where we have this bar A, okay, then it is rotating with the angular velocity. Then pag nag-rotate siya, so we have the displacement of your slotted rod. So as it rotates, it has a corresponding up and down ng displacement ng rod na ito. Okay, we have this rod, so we have the corresponding displacement as the bar A. So this one, okay. So as it rotates to its angular velocity. So we have the motion, we have reciprocation motion, which is up and down. So we have now the repetitive motion. We have this an example of a simple harmonic motion. So we have the displacement going up and down. And also you will notice here we have the corresponding displacement, which is your x. So that will be the displacement reciprocating up and down ng bar na S natin dito. So it corresponds to this one also corresponds to the x-axis we have here. Okay, so that will be the x at this side. So we form here a right triangle at this side. Now, you will notice here, now, so representing this one of coming yung ito, which is coming from this side, we form here a right triangle. So we have your bar A that is from point O to point P. Now we have here your corresponding theta. Okay. So we have the displacement, which is your x. Now to get the value of your x, so that will be, so this is already the opposite, and this is already your hypotenuse. So we use the trigonometric function. So we have now your sine of theta is equal to your opposite, that will be your x, divided by A. Now, to get the value of x, we have your x is equal to the sine of theta times the value of A, times A. Or let's say we can express this one also, this one, where your theta is equal to the angular velocity times time. So substitute that one, we have now A sine of theta, where the value of theta is the angular velocity times time. Okay, so yun yung pinanggalingan ng equation na ito. Okay. So take note also take note now, class. So the angular velocity, this one, so we have the unit. So ang unit natin, we have your units. So that will be radian per second. It will be radian per second. Okay. Where our time, the unit, is in seconds. Okay, so take note of that one. Now, to get the velocity of the system, or let's say the velocity of the mass at the given time, so that will be the derivative of the function of time. Now, to take the derivative of the function of time, so we have your derivative of x to the function of time, so we have dx over dt, which is now equal to your a sine of theta. Okay, so the derivative of that one, so that will be also your sine of theta, okay, a sine of theta, which is equal to a sine of the angular velocity times your time. So where, or let's try to remember from your calculus, no, going back, so where our d over your derivative in the function, so we have your sine of u, which is equal to the cosine. Okay, so you can still remember that one. Sorry about that one. So we have here u. Okay, and we have the derivative of your theta. Okay, so that will be your angular velocity, your time. So this is equal to your angular velocity times 1. So where your t, that will be 1 minus 1 dito. So that will be equal to the angular velocity. So that will be, this is what will be 0, cancel out. So we have your 1 multiplied with the angular velocity. It will be the angular velocity. Now, we do the derivative by chain rule. Now, derivative by the chain rule, we have the derivative of your x to the function of time, which is equal to your a, that will be multiplied by the derivative. Okay, so derivative of we call this sine angular, okay, times the time, then derivative function of x the function of time multiplied by the angular velocity, then times time. Now, our derivative of this one, derivative of x, so the function of time, of sine angular velocity times time, so we have that is now equal to a cosine, so this one, okay, so that will be the angular velocity times time. Okay, then the derivative of your theta, okay, where your theta is equal to your angular velocity times time, so we have multiply it by the angular velocity. So the velocity, so the derivative of x, the function of time for our velocity, is equal to a cosine of we call this the angular velocity times you have the angular velocity here. So that will be the velocity of the mass. Or we can rewrite it natin with this form. This is your a times your angular velocity, then we have your cosine angular velocity times time. Okay, so we can rewrite natin sa ganyang form. Now for the acceleration, so we take the acceleration of the mass. So we take the second derivative of the velocity. So we do the second derivative. So that will be the symbol of the function of time. So we have for this a, so angular velocity times your cosine angular velocity. Okay. So again, we have the derivative of du. So we have your derivative of your cosine u. So that will be negative sine of theta. Let's say this is u. Okay. Then we have the derivative with the function of time of your values of your theta. Okay. So the same also that we have done before. So that will be angular velocity times your 1. Then we have your time, that will be 1 minus 1. Then this is now equal to your angular velocity. So by derivative, by chain rule, so we have the second derivative, okay, the function of time of your velocity. So we have your a times your angular velocity. So multiply derivative of x, the function of time. So we have your cosine times your angular velocity times time. Then it is derivative of x, so the function of time, multiplied. So we have your angular velocity, we have your time. Okay. So by chain rule, so combining that one, so the second derivative function of time is equal to your a. Now we have your angular velocity times your negative, so this is the value cosine here. So we have negative sine, okay, sine of your angular velocity times time, then multiplied by the angular velocity. So we say that, rewriting our equation again, so we have your negative a times the square of, multiply this one, we have the square of the angular velocity times sine of your angular velocity times time. Okay. So we have now the second derivative value, where take note that so where the value of a is equal to the value of x. So we have the value of x, which is equal to a sine of angular velocity times time. Okay. So we can rewrite our second derivative here, function of time. Okay. So substituting the value of x this equation, so we have your negative angular velocity squared times your x. So we have now this the angular the acceleration of the mass. So our equation here for the acceleration, so you will notice here, class, that our acceleration is directly proportional to the displacement. So if we change the displacement, or let's say we increase the displacement, also the acceleration here also increases. If we're going to increase the values of this x value of the displacement, the acceleration is also increases. Okay, so that is directly proportional. Now such an vibration, which is we call it where acceleration is proportional, so proportional to the displacement and directed toward its position, so it is mostly known as a simple harmonic motion. So that's what we call it. So if we have a vibration, which is your acceleration is dependent on the displacement, so it is called a simple harmonic motion. So the motion that is being given by the x, so where a is equal to sine the angular velocity times time, so is an example of a simple harmonic motion. So we have here the example of the simple harmonic motion. Okay. And also the figure that is being shown here, I shown here before. So this is similar to call it a simple harmonic motion between cyclic motion and sinusoidal motion. Okay, that's it.